Welcome to the chi-square tutorial. This is a scary looking formula, as you can see, but it is on the AP test, which means that we want you to be very comfortable using it. And we're going to start out by using it with the fruit fly lab. I'm going to go through the process and the meaning of this test, and then at the end do a sample calculation. When I'm done, I want you to try to do the calculation with your own data, and then you can come in and ask questions tomorrow. So the purpose of the chi-square test in science is to evaluate if the outcome of an experiment is statistically significant. Sometimes things just happen due to chance, and we need to be sure that if we get results in our experiment, it's because of a valid reason and not just random chance. So, for example, let's say a friend of yours wants to flip a coin and have you predict out of 10 times that they flip it, how many times will it land on heads? What are you going to predict? Most of you are thinking, well, there's a 50-50 chance it'll land on heads, so out of 10 times, I would predict that about 5 times it would land on heads, and the other 5 it would land on tails. Well, let's say that your friend flips the coin, and instead of getting the expected 5 heads, 5 tails, maybe all 10 times the coin lands on heads. You would want to know if that's statistically significant. And you're probably thinking in your head, something's got to be wrong here because that's just not likely to happen. If you did this math equation, it would show you that that is unlikely to happen and that there's probably something else going on besides just random chance. And then you'd go investigate. You'd say, hey, let me look at that coin, and lo and behold, it's a magic coin and it only has heads on both sides. And there you have an answer for why your results deviated from what you expected. There's some terminology that goes with this test. It's called the null hypothesis. Whenever you do any kind of a chi-square test, you make this null hypothesis. And this is different from the hypothesis that you made when you're doing the experiment. This is a standard hypothesis that says that there's no statistically significant difference between the observed and expected data. You're going to predict that what you observe and what you expect, any differences would be due to just random chance. So if we use our coin example and you predict 5 out of the 10 times it'll be heads, and then instead 6 out of the 10 times it is, probably that's not just statistically significant. That's just due to random chance. So your null hypothesis is going to predict that. However, if you go through and do your chi-square test and find out that the data does vary too much, like that time where we said all 10 times it landed on heads, that's when you come up with an alternative hypothesis and you reject the null hypothesis. So let's apply this to your lab. Here's your choice chamber with your fruit flies, and remember, one end is A and the other end is B, and you've got kind of a midway mark here. We'll kind of draw it here. And you had about 30 flies in there, and you're counting how many flies after 5 minutes being exposed to a substance at the end of A and a substance at the end of B, You're going to count how many flies are on side A versus how many flies are on side B. The null hypothesis would predict that the fruit flies would be evenly distributed on either side of the choice chamber. So out of 30 flies, we would expect 15 on side A and 15 on side B due to random chance. No matter what we're putting on the ends, the null hypothesis is always going to predict that we're going to get results that are just due to random chance and nothing significant altering them. However, when you did the lab, you probably, for certain substances, saw different values than that. So I'm going to do a couple calculations with you to work through that. So let's say when you did water, the distilled water on side A and the distilled water on side B, let's say you came up with 17 flies on side A and 13 on side B at the end of 5 minutes. So what we would do is we'd say chi-squared equals, and that sigma sign is the sum of the results, and we have to factor in our side A results and our side B results. So we're going to add up what we saw on side A. We observed 17, but our null hypothesis said that we predicted we'd have only 15. And we square that number and we divide by what we expected or predicted, which is 15. Then the sum part means that we're going to add to that the same calculations for side B, for those 13 flies. There we observed 13 flies minus we expected 15. We square that and we divide by 15. So now our chi-squared is equal to 17 minus 15, which is 2 squared over 15, plus 13 minus 15, negative 2 squared over 15. So that's 4 fifteenths plus 4 fifteenths equals 8 fifteenths. And when I plug that into the calculator, I get 0.5333, etc. So we'll simplify that to 0.53. Now we have our chi-squared value. Now there's this table that we have to look at to figure out if that chi-squared value is, if it's telling us that our results are significant or not. So that's our chi-squared value. So in order to use this table, now you have to figure out the degrees of freedom. And all this is we are taking into account the number of possible outcomes in our experiment, and then we subtract 1 from that number, and that gives us our degrees of freedom. So in our experiment, for each fruit fly, the number of possibilities for them was they could either go to side A or side B. So that gives us 2 possible outcomes. So what would our degree of freedom be? Would be 2 minus 1 equals 1. So now we're going to come to this column, the 1 column. We're going to look at this row, probability P equals 0.05, and I'll tell you on the next slide why we use this row, but it's shaded in because in science that's the row that we usually use. And where they meet at 1 degree of freedom, the critical value is 3.84, or the chi-squared critical value is 3.84. And what this means is that if our chi-squared value is greater than or equal to that critical value, then the null hypothesis is rejected. If our calculated value is less than that number, then we accept the null hypothesis. So for our distilled water experiment, our chi-squared indeed is less than 3.84. So we would accept the null hypothesis, and if you recall, our null hypothesis said, oops, there it is, said that we would expect the flies to be evenly distributed due to random chance. So we can say for distilled water that that is true. The distilled water must not be affecting them because they're just randomly ending up on either side. Okay? So that would be one calculation. Now, let's think about some substance that you tested where you did seem to see a significant difference. So let's say on side A, when you tested a certain substance, you saw of your 30 flies, 28 of them on side A. And then B had your distilled water and had only 2. So now we would go through and we'd do the same calculations using those numbers. So chi-squared is equal to the observed, so 28 minus our expected 15 squared over 15 plus, we have to sum the two possible outcomes, so plus 2 minus 15 squared over 15. So this simplifies down to 13 squared plus negative 13 squared over 15. So go ahead and calculate that. So 169 over 15 plus 169 over 15 equals 338 divided by 15 equals 22.5. 22.5333. So 22.5. And when we look at our table, we're still working in 1 degree of freedom. 22.5 is way bigger than 3.84. So now we're in that situation where it's greater than, we would reject the null hypothesis, which means we have to come up with an alternative hypothesis. And so you would say that something in substance A must be attracting the flies. They have a positive chemotaxis toward it, and you would now further investigate why. Now to explain why we use that number 0.05, this means that those results that you got would be significant at a probability of 0.05, meaning that only 5% of the time would you expect to see similar data if the null hypothesis was correct. Which, for me, it's easier to think about, okay, well that means that you're 95% sure that the data do not fit the null hypothesis. 95% of the time, they're not fitting the null hypothesis. So that gives you 95% confidence in your data. So that's why we use that row in the chart. Because if we're 95% confident, then we can say that it's statistically significant. So for the first calculation, it wasn't statistically significant. We accepted the null hypothesis that it was random chance. For the second calculation, it was definitely statistically significant. We had to reject the null hypothesis. It was not due to random chance. And we now have to consider reasons for the variation, additional experimentation, repeat it to confirm, explore why they were drawn to that substance. So you can see that this would be a good test to do anytime that you're getting quantitative data and you want to figure out if your results are significant versus just random chance. Scientists use this all the time when they're doing experiments and they're writing papers. You'll see calculations where they'll talk about with the p equals 0.05 whether their results were statistically significant or not. And